So let us start this session. So today's session will be more on the problem solving, and I have selected few problems from Pekenag, the book on power plant engineering, and these problems are related to steam turbines and gas turbines. So once again, my name is Tanmay Sharma, and I am the TA of this course, NPTEL course, and I'll be solving the problems along with you. So let us start this session. So first of all, I want to just refresh your memory. So I'm showing here the impulse and reaction turbines, how it exactly looks like. So this is an impulse turbine, and you see that there is a nozzle, and in the nozzle the pressure the gas expands, and accordingly the velocity increases. So this high velocity this steam, it goes into this moving blades, which are actually are fixed to the shaft. Okay, the moving blades are fixed to the shaft, and then again it passes through the nozzles, which are fixed to the casing. So the shaft, it is rotating, and the moving blades are fixed to the shaft, and these are the nozzles which are fixed to the casing, which is above the shaft, and it is static. So you can see that when it is moving through the moving blades, then the velocity of the steam, it decreases, but the pressure remains constant. So that is the fundamental concept of an impulse turbine. Okay, then again it moves to the nozzle, and it utilizes some amount of pressure, and the velocity increases as the pressure decreases, means the gas is expanding, the velocity again increases, then again it moves to the second set of moving blades. Again the velocity decreases in the blades, but the pressure remains constant. So the impulse that is generated onto the moving blades, it is due to the velocity difference and not due to the pressure change. It is happening at a constant pressure. So this is the fundamental concept of an impulse turbine, and here I am showing a pressure compounding. So you can see that there are various stages of moving blades and nozzles, right? So these are compounded. When there are more than one set of moving blades, then it is called a compounded stages are present. So this is a pressure compounded, because the pressure at each of these stages, we're utilizing the pressure, but we have an option that we may not be expanding the gases, the pressure we may keep it as constant. Okay, so if that is kept constant, then it is simply a velocity compounding, and these are also called as the Curtis stages. Okay, and the pressure compounding are also known as the Ratu stages, or Ratu compounding. Then we have the reaction turbine. So the difference between a reaction turbine and an impulse turbine is that when it moves through the fixed blade, the pressure, yes, it decreases, the steam expands, and accordingly the velocity increases. But in the moving blade, the pressure does not remain constant. It is also giving some reaction to the moving blade. Okay, so the moving blades are actually aerofoil shaped. So in an aerofoil, by aerofoil I mean that the wings of a plane, right? So it actually a upward force is exerted upon the wings, okay, because of the shape that it has. So these are the airfoil shapes. So the moving blade also is made in such a way that the steam that is flowing through the moving blades, it also imparts a reaction force onto the moving blades. So that is why the pressure, it decreases, and also the velocity is also imparting the is also contributing to the whole tangential force on the blades. So that is why the pressure, as it does not remains constant, it is also imparting a reaction. So that is why it is called a reaction turbine. So these are the two types of classifications of turbines, and we'll be focusing on today's session about the impulse turbine and the impulse reaction turbine. So the impulse reaction turbine will be focusing Parsons turbine, and in impulse turbine we'll be considering simple impulse turbines and Curtis staging, what will happen, how can we calculate the diagram efficiency, the power output, and everything. So we will talk about that. We will solve few problems on that. So now let us start. As I have already told that I'm referring the book Power Plant Engineering by P.K. Nag, and these are the exact question numbers that you can see. That is the 7.9. If you go and see the 7.9, that is the exact problem. So this is a very good book. You can go through it, and I hope that after this session, more of the concept of how to solve the problems will be clear. So the first question is a very simple problem. The velocity of the steam entering a simple impulse turbine is 100 meter per second. So from the nozzle it is coming at 100 meter per second, and the nozzle angle is 20 degree. Okay, it is directed at 20 degree. The mean peripheral velocity of the blades, so velocity of the blades, that is, it is rotating, it is at 400 meter per second, and the velocity and the blades are symmetrical, means the inlet and the outlet angles are the same. Inlet to the blade angle and the outlet angle to the blade, these are same, means the beta 1 and beta 2 will be same. Then if the steam is to enter the blades without shock, what will be the blade angles? And then it is said that the first one is the neglecting the friction effects on the blades, calculate the tangential force on the blades and the diagram power for a mass flow of 0.75 kg per second. The steam is flowing at a rate of this, it is given. Then estimate also the axial thrust and the diagram efficiency. So let us start this problem. So first of all, the blades are symmetrical, so beta 1 and beta 2. First of all, let me explain the velocity diagram a little bit. What happens is that the steam, you just focus on these arrows as a direction, because it's a vector, right? The velocity is a vector, so you consider it as a simple direction of the steam. So you can see that the steam, it enters along this line, so v1 is the vector, but also the blades are moving in the same direction here, means from this point to this point, so in this direction it is moving. So that is why the relative velocity will be somewhat less than v1, right? So that is why we will have to retrace it back to this particular point, and the second line will be the relative velocity vr1. So v1 is the actual velocity, means we are supplying to the blade. vr1 is the relative velocity by considering the movement of the blade also. So these angles are different. The alpha, it is the inlet angle, the nozzle angle, so it is 20 degree, it is given. Beta 1 is the relative velocity angle, so at which angle it is being inlet to the blades. So this is the inlet part of the blade. Then the exit part also, so it will move out from this blade, right? So it will move out according to this arrow that you can see. So this is the relative velocity vr2. So by vr2 value, it is moving out, but the turbine is also moving in this direction, right? So we'll have to minus subtract the value of the turbine speed, so that we can get the actual velocity in which the steam is exiting the blade. That is why we'll have to go from this point to this point, and if we draw a vector like this v1, so we will get this actual exit velocity. So this is also a very important term, because this is v2. The v2 is the exit velocity. So this is very important when we will be doing staging. So from one stage it is going to another stage, so we'll have to consider angle. The initial angle may be alpha, but the final angle may be different than alpha. So we'll have to evaluate the value of v2 and accordingly evaluate the values of this delta. So we'll be talking about that next. Now, so the thumb rule is, since we are solving the problem, I will tell you about a thumb rule. First of all, in any case, we'll have to measure the angle beta 1. So we may be knowing the alpha value, but the beta 1 is unknown, so we can measure that. How? Because we know the value of the blade velocity, the velocity at which the blades are moving. So the sine component, if we know the sine means if we means separate the components of the v1, this is the vector v1, and the vr1, we will know that. So vr1 sine beta, so this component, the vertical component, this is same for the both, so that is why vr1 sine beta 1 is equal to v1 sine alpha. And accordingly, if we see vr1 cos beta 1, so that is, so if we from this point to this point, the whole vector, so if we that will be v1 cos alpha 1, the whole vector. If we subtract the value of vb, we will get this particular vector, so vr1 cos beta 1. So this is the thumb rule that is basically used to calculate the value of beta 1, and from beta 1 we will calculate the value of vr1 and other quantities, because that is unknown. We know the v1 and the vb and the alpha also, because these are the design parameters. Then we calculate the value of beta 1, it is coming to be 32.35. Okay, so I made a mistake, this should be beta 2. So beta 1 and beta 2, these are equal, right? So we got the value of the beta 2 also, the exit velocity, the exit angle of the relative velocity. Then we need to calculate the vr1. So we know from this particular formula directly we will get to know the beta 1 we knew, alpha we knew, v1 we knew, so accordingly we will get the value of vr1. So you might be a little bit curious that the value of vr1, so it is less than the actual velocity of the nozzle. Why? Because we are considering the velocity of the blade also, right? So the relative velocity will be a little bit less. And since the blades are symmetrical and there is no, I think there is no friction effects neglecting the friction effects, so we will directly have this vr1 equals to vr2 and 39.25. so this is the case for symmetrical blades, but and neglecting the friction. But we'll also solve one problem where we consider the friction effects. So what will be the changes, I will show you then. So the net axial velocity difference, so axial velocity difference, so axial, I think it is the world velocity difference. The net world velocity difference means the velocity difference in the direction of the blade moving, the tangential direction of the blade movement. So that is I am calculating here. So here vr1 cos beta 1, so the vr1 component, vr1 component, so that is contributing to the blade movement, and vr2 component. So since the vr2 will be in a different direction, I will show you here, it might be more clear then. So you can see that here the blade it is coming inside, right? The steam is coming inside the blade, right, like this, and the relative velocity outside is moving backward, but the blade is moving in this direction. So for this we'll have to subtract the value of vb to get the vr1, and here since we are already getting vr2 but it is in this direction, so the net velocity of the that is tangential to the blade, so that is vr1 and minus vr2. so since the vr2 is in this direction, so the component of vr2 in the opposite direction will be negative, right? So we'll have to use that component, and then we'll have to subtract, so the resulting part will be the addition of the two components. But that is not the same for the axial part. In axial what happens is that the component of the velocity which is entering into the blade will be from left to right, and the component of the velocity which is exiting the blade will also be left to right. So the both is positive, and hence we will have to subtract that. Okay, so that is the fundamental concept. So here the net world velocity would be directly to vr1 cos beta 1, and we got this value. So this is the velocity that is responsible for the movement of the blade and the power output. So we will see that. So here actually I am calculating the axial velocity. The va is the axial velocity. So what is axial velocity? So the steam is moving inside the blade, so it will flow across the blade, right? So it will there will be one tangential component which is moving the blade, and there will be one axial component which is simply passing away. So that is contributing to the jerking or the thrust uh, in the turbine blades. So we'll have to calculate that, and that can be calculated by this vertical component vr1 sine beta 1 and the vr2 sine beta 2 in this direction. So since vr1 beta 1 these are all same, so we will get a axial velocity 0. So actually axial velocity should be 0 in order to get the least amount of jerk. So if the turbine is actually vibrating now, so that is mainly due to the axial velocity component, and the turbine is rotating, that is due to the world velocity component. The vw is responsible for that. So tangential thrust, which is generating the power, is simply mass into mass flow rate into the velocity. So that is the change in momentum. So that by that we will get this particular force. And the diagram power, so by diagram power what do we mean is that we took the help of the diagram, this velocity diagram, to calculate the velocity components and everything, right? But the velocity components may be a little bit different than the diagram. So since we are referring to the diagram, we are simply giving this as wd pt into vb. So simply we are calculating the pt and the vb, and from the diagram, hence the power is this in kilowatt. Now why did we do this? The amount of the world velocity, and it is moving with a speed of vb, the blade is moving with a speed of vb in this circular direction, right? And what is causing this? The tangential thrust, right? So that is where force into the velocity that will give us the power, which is rotating the blade. And the diagram efficiency is simple, the diagram power divided by excuse me, is there any question? Is there any doubts? Any question? Okay, then I'll move on. So wd divided by this amount entity. So what is this entity? So this is the kinetic energy of the steam which is entering into the blade, right? So the whole kinetic energy, from that we are actually producing some amount of power. So how much percentage, that will give us the diagram efficiency. So simply we are dividing it and we are getting 86.4%. So then the axial thrust, okay, the axial thrust is based upon this velocity difference, and that is equal to 0. And in the second case, what is given is that the relative velocity at the exit is reduced due to friction. So first we saw that the blade was symmetrical, okay, the beta 1 equals to beta 2, and also there was no loss. So that's why the velocity of the steam inlet, relative velocity, is also equal to the velocity of the steam outlet. If there was friction, then what would happen? It would reduce the velocity of the steam, right? So vr2 will be lesser than vr1, and also it will means the friction will also cause rise of this energy, means the heat. So the heat will be lost due to friction. So these are the two main causes, and the friction is always, it is not avoidable. So we are considering here 0.8, and hence the vr2 is a little bit less than vr1. We are calculating by this particular formula. Then the net world component is now a little bit modified. It is 972.06, and which would be a little bit lesser than the previous case, okay. And where is the other the change is utilized? So actually the change is utilized in the axial thrust due to the friction, as it is rubbing the blade. So you can imagine when something is rubbing or gliding with a particular thrust to the surface, then it is actually imparting a particular force in that direction. So that is the axial thrust. So the vw, it is now not 0. There is some component, okay. So due to that component, the axial thrust is being produced, and that is pa equals to 51.3 newton. That this will be actually giving a jerk or the vibration to the turbine in the axial direction. Then we calculate the diagram power by the same concept, and the diagram efficiency also using the same concept. So that is the first problem. So before moving on to the next problem, I want to introduce a concept, the reheat factor in steam turbines. So as I was talking that friction and everything is happening, means it is taking place, it is not avoidable, but yes, it is reducible but not avoidable. So that is why so we have to consider in our calculations the effect of this friction, the effect of this heat losses, and accordingly due to the heat losses, what is the entropy is changing, so effect of this entropy change. So that is reflected in this particular diagram, you can see. So actually this diagram represents a multi-stage steam turbine. Okay, so there are many stages. So this 1 to 2s, between 1 to 2s there is one set of blades. Then it is again expanding, and it is again going through the second set of blades, that is 2 to 3. Then again 3 to 4, that is between the pressure to 3 to 4 there is another stage. So accordingly there are various stages. So here we can see there are 4 stages: 0 to 1, then P1 to P2, then P2 to P3, and P3 to P4. So there are 4 stages. Then in these stages, what happens is that the none of the this processes are isentropic. Although we consider for the convenience of a calculation, none of these processes are isentropic, and we already know about it. So 1 to 2s is an isentropic process of gas expansion inside the turbine, but due to the losses in heat, it is going from 1 to 2, this non-reversible process, irreversible process, sorry. So then again it should have expanded isentropically 2 to 3s, but again due to the efficiency it is coming 2 to 3. Same way 3 to 4s, but it is going 3 to 4, and 4 to 5s, but it is going 4 to 5. So the we are not getting the isentropic conditions, and this is because of reheat, as it takes place with the increase in entropy. So the reheat in a given stage so is available to do work in the succeeding stage, except the last stage where the reheat is a loss. So what it tells is that the energy which is liberated due to the friction losses, so it is also imparting some enthalpy to the steam, which is the outlet of this at this stage. So that enthalpy can be used in this particular the second or its succeeding stage, right? So that is why this reheating, it is actually beneficial for the succeeding stages, except the last stages, because after this we are not using the enthalpy of the steam for moving the turbine blades, but it is directly going to the condenser. That is why it is not beneficial to the last stage. Okay, so the constant pressure lines diverge from one another, thereby increasing the enthalpy drop for the same pressure drop. Yes, so you can see these are the constant pressure lines in an HS diagram. So this is enthalpy, this is S, right? So it is an HS diagram. The pressure lines, what you see is that the difference between the pressure, constant entropy line, if we draw between the pressures, so this gap and this gap is different, so it is diverging, right? So as we are moving towards the right side, it is diverging, and the drop in enthalpy, it is also increasing, right? So because of this, and the second means the heat which is added to the steam, so because of the 2 and 3, the sum of the available energies, that is isentropic enthalpy drops for each stage, that is greater than the total enthalpy total available energy, that is 1 to 6s. So if we go in staging, the total sum, that is 1 to 2s, then 2 to 3, actually it won't be 2s, so 1 to so we are considering the isentropic enthalpy drops, right? So 1 to 2s, 2 to 3s, 3 to 4s, and 4 to 5s. If we add the all these 4, so we will get higher amount of enthalpy than 1 to 6s. So that is the case. If we already we are getting some loss, but due to the loss we are also having higher enthalpy drops in the turbine. So that is the concept of reheat. Now what is exactly reheat factor? So reheat factor is cumulative isent ha, please.
जो रही रीहीट कहाँ पे होती है, मतलब बॉयलर में होती है, टरबाइन में होती है?
I'm talking about the turbines. So the
टरबाइन में तो होती है सर। जैसे एक स्टेज से दूसरी स्टेज पे जब जा रहा है तो उसमें कौन सा हीटर लगाया जाओ जहाँ पे रीहीट टेक प्लेस, मतलब होगी?
so you are getting a little bit puzzled. देखिए, see, the reheat, it is not due to any reheat, means heater. We are not supplying the energy separately. The energy is being supplied due to the friction loss. Due to the friction, some amount of energy is generated, right, in one stage. So that amount of energy which is being lost, it is being added to the steam, right? So that is being utilized in the next stage. So that is how the reheating of the steam it happens.
सर ठीक है, वो
Hmm.
फ्रिक्शन लॉस उसमें ऐड हो गया, तो उसमें प्रेशर ड्रॉप होएगा ना? आप इसमें रीहीट करने के बाद प्रेशर राइज हो रहा है इसमें आपके ग्राफ में।
Pressure, where is the pressure rising? It is,
प्रेशर
this is a constant pressure process, na? P1, then P naught. So according to the constant pressure process, it is getting a little bit of enthalpy. So the enthalpy at this point and this point, these are the 2s enthalpy is lesser than 2, right? So actually it would have been gone to 2s, but now it is going to 2 because it is getting some amount of enthalpy for the reheat due to the friction losses. So that
सर।
so this is the reheating. We are not using any heaters, and the reheating Rankine cycle, that is quite different. So that is we are using the different stages, and we are going to the boiler, we are heating the steam, and then again coming to the turbine. So that is completely different. This is due to the is internal friction losses. It is getting some heat to this second stage or the next stages, but that is only beneficial to the first few stages, but not to the last stage, because in the last stage whatever enthalpy is gained, that is actually going to the condenser, it is being lost. Okay. Okay, then I was talking about the reheat factor. The reheat factor is the cumulative isentropic heat drop of each stage. Cumulative means if I add 1 to 2, then 2 to 3, 3 to 4, and 4 to I am talking isentropic, right? So 1 to 2s, 2 to 3s, 3 to 4s, and 4 to 5s. If I add this all and then I divide it with the total isentropic heat drop, so I was considering the pressure P0 and P4, right? So if it is isentropic process, it would have gone 1 to 6s between the same pressure difference. So that would have been 1 to 1 minus 6s, right? So this is the whole part. We have adding the pressure means isentropic heat drop at each cases divided by this, and since it is diverging, the pressure is diverging towards the right hand side, we are observing the RF will be always greater than 1. It will be always greater than 1. Okay, now let me prove to you, let me compare with the internal efficiency. Okay, so for internal efficiency, what we'll do first, we'll calculate the stage efficiency. So we know the stage efficiency of a turbine. So h between, suppose I will take the example of this 1 2 1 2s. So this is the total enthalpy drop we should have got, but in the the drop we are getting is 1 to 2. So h1 minus h2 divided by h1 minus h2s. So that is the one I'm writing, h1 minus h2, that is less. And what should have we got if there was no friction? h1 minus h2s. Similarly, for all the cases, if I assume that the efficiency of stage is constant, let us assume, but that may not be the case, let us assume. So if I assume now h1 minus 2s, it will be equal to the h1 minus h2 divided by eta stage. So each of the enthalpy drop, isentropic enthalpy drops, so that would be equal to the non-isentropic means simple irreversible adiabatic drop divided by the eta stage. So we can convert this whole equation into this particular equation, right? h1 minus h2s, that can be h1 minus h2 divided by eta stage, and we are considering eta stage to be constant for all the stages. So accordingly, if you write and we take the 1 by eta stage common, then h1 minus h2, then we'll add all this up. So h2 cancel, h3 3 cancel, 4 cancel, so we'll be left by h1 minus h5. So 1 by eta stage into h1 minus h5 divided by h1 minus h6s. So what is that? h1 minus h5, so h1 minus h5. Okay, so let us now consider that there is no pressure staging. Okay, so what we will get, since it is having some this internal this efficiency, so it will expand from 1 to 5 rather than isentropically from 1 to 6s. So the efficiency of the whole thing would be what? h1 minus h5 divided by h1 minus h6s. So that is what we are getting, 1 by eta stage into eta eternal. That is the whole case, right? So RF is eta eternal divided by eta stage. So we'll use this particular formula in the next problem that we have. So that is why I wanted to give you this particular concept. Okay, so let us move on.
Hello.
Yes.
Hello, good evening, sir.
Good evening.
In that input factor image, there is a line stating that condition line like that, the dotted line.
Dotted line, yes.
Condition line it is there, no, sir.
Huh.
So what is the condition line, sir?
The condition line means actually it is I think it is stating the condition, the actual condition. So it is nothing that first of all the dotted is because of the irreversibility, because it is not isentropic, it is means not reversible, so that is why we are using dotted line. But this is the actual condition that it is happening. If we directly expand from 1 to 6s, actually we would go by this process. So that is the actual conditioning line, I think.
So that is where the actual process is going on. So that's why it is a condition line.
Because we are expanding from 1 to 6s now, so this is the process that it would take. And if we are not looking much depth into p1 p2 p3 or any staging, we just have a turbine. We are not looking into the staging part, then we'll actually know the 1 to 5 and rather than 1 to 6s. So 1 to 5 is, that is why it is called as the conditioning line.
Okay, sir.
Okay. So let us move on to this problem. So an impulse turbine, steam turbine, has a number of pressure stages. Okay, each having a row of nozzles and a single ring of blades. Okay, the nozzle angle in the first stage is 20 degree and the blade exit angle is 30 degree. So we are given the nozzle angle and the blade exit angle with reference to the plane of rotation. Okay, the mean, so we are given the alpha value and the blade exit angle, that is the beta 2 value. Okay, then the mean blade velocity is 130 meter per second. So this particular part from here to here, this is 130 meter per second, and the velocity of steam leaving the nozzles is 330 meter per second. So the taking the blade friction factor as 0.8, so here we need to consider friction. So that is why the VR1 and VR2 will be not the same, and the nozzle efficiency of 0.85. So nozzle efficiency is given. Good. Determine the work in the stage per kg of steam and the stage efficiency. So let us focus on the first part. So here, as per the thumb rule that I have already stated before, we'll first equate the sine components and equate the cos components, and then we will get the tan beta 1. So I won't go into that. So accordingly we will get the value of beta 1, that is 32.75. okay, so here after this, after knowing the value of beta 1, we will find the value of VR1, relative velocity at the inlet. So that would be equating the sine components, we will get this value as 212.53. Then from this since we are given a blade friction factor, so the velocity of the steam entering will be 0.8 time the velocity of the steam exiting will be 0.8 times the velocity of the steam entering. That is why we will be multiplying the factor 0.8 and getting this particular value of VR2. So VR2 we have calculated, VR1 we have calculated, V1 we know, so then the world component we calculate the VW. So simply VW is what? VR1 cos beta, the cosine component of VR1 and VR2. So this is VR2 cosine component, the whole part, and VR1, sorry, am I making a mistake? So VR1, the cosine component is this one, and VR2 cosine component is from this to this one. So this we are adding, so this is total VW, and the world component is responsible for the blade rotation, so that is equal to 372.334. Okay, we have calculated the world component. So if we know the velocity which is responsible to blade movement, and we know the blade velocity at which it is moving, and we know the mass of the steam, then we can calculate the diagram power. So that is given as this the multiplication of the three components, and accordingly we have this much kilojoule per kg of the steam. So per kg, since we are considering per kg, so we are taking Ws as 1, right? We are not given, so let us calculate the whole thing per kg of steam. Then the diagram efficiency would be so this is the diagram power, so Ws is 1, right? Also here would be a Ws, so these two will be cancelled out. The inlet velocity, inlet kinetic energy, then the ratio would be 78.15%. So that is the diagram efficiency. Then, so that was the diagram efficiency, but we are also having a efficiency of the nozzle, right? So there will be some losses in the nozzle also. So accordingly, if we consider the boat, then the stage efficiency will be 66.4%. Then for solving the next case, we need this reheat factor. So the next case is if the steam supply to the first stage is 20 bar to 50 degrees Celsius. Okay, the so that this is the case actually. Let me so I will come to the figure later. So so the first stage is at 20 bar to 50 degrees Celsius, and the condenser pressure is at 0.07 bar. So from 20 bar it is expanding up to 0.07 bar. So we need to estimate the number of stages required, assuming the stage efficiency and the work done are the same for all stages. So that is completely means going as per the concept that I have just given. So we need to have the total enthalpy drop. Okay, so if we need if we have the total enthalpy drop and the enthalpy drop in each stage, then we can calculate easily the what should be the number of stages. So that is why it is given a reheat factor of 1.06, and we'll use this particular formula that we have given. So n eternal so Rf was equal to eta eternal by eta stage, right? So eta stage, all the stage that we know is 66.4%. so the whole of the process that would take a the whole process would be 70.41% efficient, just multiplying the reheat factor. Okay, since because we are getting some amount of available energy from the reheat, right, due to the friction losses, so that is why its efficiency a little bit it has increased. Then from steam table, now we will use this particular chart. So we know that this is this was the point 1, and this is the point 2s. So we will take the steam table here. The value is h1. This we will take from 250 degrees Celsius as 20 bar. So from the steam table you will get this value. Similarly, we will get the S1 entropy, and we know this is a constant entropy line 2s. So that is why we will calculate the 2s. Means it is equate, and the 2s will be given as due to the dryness fraction. The dryness fraction, while considering the dryness fraction, we will get this particular value. So this is the SF at 0.007 bar, and this is the SFG at the same. Accordingly, we will get the dryness fraction. So we have already calculated this in the Rankine cycle. I hope you remember. Then we calculate the enthalpy at this particular point. So enthalpy is by this formula we will get this much is the enthalpy. So yeah, the enthalpy 2902 at the point 1, and H2S, if it is an isentropic process, then it is 2031.29. But our process is not isentropic. Here we are not considering any stages. There were number of pressure stages, right? So we are not considering the pressure stages. We're simply considering a one turbine and what is its total internal efficiency. We are not considering the efficiency of the each stage. So using the reheat factor, we already know the efficiency of the whole turbine. That is the internal efficiency, this part, right? So that is why we needed the reheat factor and the concept, and accordingly we will calculate the enthalpy at this point 2. So that is actually we need only H1 by H2, so we calculated directly the del H. So total del H is 612.57, and now if yeah, we divide it by the enthalpy of each stage that we calculated before, and we will get total 15 stages. So total 15 stages we require to drop it from 1 to 0.2. So that was the problem, and that is how we have used the reheat factor concept. Next, I want to quickly cover this part, the Curtis compounding. Okay, suppose you are given the two types, means a Curtis compounding. So let me talk about the Curtis compounding first. So it is actually a velocity compounded impulse wheel. What happens is that are you able to see this particular figure? So here this is a particular schematic of a velocity compounded impulse wheel. What happens is that the blade moves from this the steam moves from this fixed blade and moves onto the moving blade. Okay, so first of all, the what happens is that the velocity, the pressure, the pressure, so this velocity and the pressure, this is the steam pressure line. The upper line is the steam pressure, and the steam speed is this particular line. So you see that the pressure first decreases in the nozzle, so it decreases, and then the velocity, it results in the increase in the blade steam velocity, and this the steam which has been reduced in this particular part, it remains constant throughout the whole means the stages, whole of the stages, but at each parts the velocity is reducing. So in the fixed, there will be no reduction in the velocity. Okay, it will remain constant, but again it is moving into the moving blade section, so again the steam speed will decrease, but the steam pressure is remaining the constant. So this is the concept of a Curtis compounding or velocity compounded impulse wheel. But if we had pressure compounding, what would have been the scenario? The pressure would have decreased in each of the fixed blade cases, because we are supplying means we are giving a nozzle and the gas is expanding in there, so the pressure will decrease and the velocity will increase. So this is the velocity compounded, and previously we talked about the this pressure compounded. So this is a problem related to the two-row velocity compound impulse wheel. Okay, so if we have two rows, can we use the information of the first row or the first nozzle inlet condition and derive the whole part or get till the last part? So let us see from this point. So these were the cases, and let us start the problem directly. So first of all, we will consider the inlet, the first fixed blade and the moving blade case. So from the nozzle to the first row of moving blades, so this is the velocity diagram, and yeah, going through the thumb rule, we calculate the beta 1, so that is the relative velocity angle, right? Then we calculate the inlet relative velocity, similar, and then using the this blade friction coefficient, we calculate the outlet relative velocity. Okay, we have the outlet relative velocity. Then from the exit of the first row of moving blades to the fixed blades, so first row of moving blades to the fixed blade, that is the outlet part we are talking now, the delta 1. So this is a new part, so this is delta 1. Okay, so this delta 1 angle will actually be used to supply the steam to the next or the second moving blade conditions. So this is the outlet of from the blade, actual outlet. Okay, so that we calculate by directly first we actually calculate the v2 cos theta and equate it with this vr2 and sorry vr2 vr2 this part and the cosine part. If we separately equate the components, just going by the thumb rule that I previously discussed, we'll directly get the value of tan theta, tan delta 1 and accordingly delta 1. So this is similar to the previous concept, previous thumb rule. Then accordingly we are simply equating the sine components and we are getting the velocity v2. This is the v2. Okay, and v3, yes, as it is moving through a fixed blade, but still it is a blade, right? So in the blade there is a friction coefficient and accordingly its velocity will reduce, and we are getting the final outlet velocity as 255.9. So this velocity will be directly given to the second row of moving blades. So before moving on to the second blade, second set of blades, let us first calculate the whirl and the axial component. Is there any doubt?
Hello, sir. Actually, in the blade friction coefficient, we used to get it for relative velocity now, sir.
Yes, yes.
So, could you please move to the before slide, sir? There, V3 equal to 0.85 V2 they have made. It must be relative velocity now, sir.
You're right, right. But what is the condition now? The steam is now moving from this moving blade to the fixed blade. So this blade is not moving, right? So whatever steam is inlet, that will be the and what is the velocity of this? 0, right? So we need not subtract anything from the inlet velocity. Are you getting? Here, here the velocity was this was moving, right? So we have to consider this velocity to calculate the relative velocity. But now the relative velocity and the exit velocity, it is same, right? So the v2, which is from the exit of this particular blade, it is gliding over the fixed blade, right? And then the output of this fixed blade, that is v3. So as it was gliding in a blade, so it would have some friction and accordingly its velocity will reduce.
Yes, sir. Okay. Thank you.
This is a very good question. Why we are not considering the relative velocity? Thank you for the question. So next we will be calculating the whirl component and the axial component. So in each of the moving blade cases, so there will be a whirl component which is rotating the blades, and there will be an axial component which is actually vibrating the blades. The axial component will be from left to right, right? So it will impact on the blade, means in the axial direction, that we do not want. So although we will have to calculate it. So Vw1 we calculate by this cosine component of the relative velocities. So we get this, and axial is the sine velocity. But here you can see we are subtracting. Here we are adding. Why? So the blade is in a U shape, right? The relative velocity is now from down to up, and here the relative velocity is from up to down. So the up to down, the component is in down direction. So we'll have to consider the negative of that component, and again the final will be the negative of that component, and we'll be subtracting, and so the minus minus goes plus. So that is why we are actually adding the whole thing, right? So the whirl component is added, the axial component, now the component of the velocity entering, that is in left to right direction, but the component which is leaving, that is also from left to right. So these are same direction, having same direction. That is why we need to subtract it. So that is why we are subtracting here. So this is the axial component. Now for the first, we have done the whole analysis, okay, the first moving blades. Now we move to the second moving blade. So we know the velocity at which it is inletting, means it is coming in to the blades. Then we calculate the value of this beta 3. So first, according to the thumb rule, we use beta 3. So alpha 1, so the fixed guide blades, so we are given a value, the exit angle from the fixed guide blade is 22 degrees, so that will be the inlet to the moving blade, right? So that is alpha 1, and accordingly we find first the value of beta 3, then we find the value of VR3, and then we finally find the value of VR4, which is 0.85 times the value of VR3. So that was the analysis to the second row moving blades. So we finally calculate the in the second blade the whirl component, same formula, the axial component also. So by that we get these values, and finally we'll have to add the components. So this is contributing some VW, and this is also contributing a whirl component. So together this much of velocity we are getting, this much of contribution to the rotation of the blades. Then this much is the contribution to the axial vibration of the blades. So that is 57.98, and together we'll be calculating the tangential thrust, which is actually the mass of the steam inlet into the velocity of that. So that is the force by which it is means is the tangential force to the moving blades, and the axial force is this much, which is being contributed by the axial component. Power developed is simply the tangential thrust into the blade velocity, and that would be the diagram power that we have. Then we calculate the diagram efficiency simply by this formula, and we get 71.39%. So actually so this is a particular homework that I want to give to all. So this is simply an impulse steam turbine, and it has the condenser pressure and everything. So you just think about this problem. You just think about this problem and do it. If you find any difficulty, then you can just contact me. And I think we are already past. I wanted to introduce to you the Parsons turbine. So I will quickly go through the Parsons turbine also. Okay, so in a Parsons turbine, what happens is it is a impulse reaction turbine, and basically it is used for marine components like ships and everything. So there you need not have a very bulky system, right? You do not need a very bulky system. Only sufficiently it should the power should be given to the vessel to move, right? So it is having actually generally a lower this amount of work output, but the thing is that it is an impulse reaction turbine. So what happens is that in the moving blades, initially in the impulse turbine the pressure was constant. At the same pressure, only the velocity was reducing, and the reduction in the velocity imparted to the turbine rotation. But in an impulse reaction turbine, also along with the velocity reduction, the pressure is also reducing. That the pressure component is also giving some contribution to the turbine rotation. Why? Because the moving blades are of airfoil shape, so there is some pressure difference that is being generated, and that is being used also. So these turbines are actually having some design conditions that first of all, it is called as the 50% turbine. Why 50% turbine? As I was talking about the impulse part and the reaction part, right? So in the fixed blade, the enthalpy will be dropped to accelerate the steam, right? To increase the steam velocity. And in the moving blades, there will be also some enthalpy drop. Okay, so the fraction of the enthalpy drop in the moving blade to the whole of the enthalpy drop in that particular state, that is 50%. So that is actually degree of reaction. Okay, so since it is 50%, we are calling it also as 50% reaction turbine. Okay, so now the design conditions in order to get the 50% is actually vr1 equals to v2. The relative velocity of vr1, that will be equal to the v2, and v1, this is the inlet velocity, will be equal to the vr2 relative velocity. Then the beta 1 will be equal to the delta this. So it is a very symmetrical diagram. Okay, it is a very symmetrical diagram, and due to this symmetry, there is no axial component existing. So delta v a, that will be equal to 0. So there is no jerking in the turbine, and which is very beneficial in such cases. Okay, so let us quickly solve this problem. So the turbine is running at 400 rpm. It develops 5 megawatt using this much this steam. So we first actually calculate what is the mass of the steam flowing. So how we do that? We know 6 kg per kilowatt hour. So how much kilowatt hour it is producing? It is megawatt, 5 megawatt. So we are just simply multiplying it, and then we are getting in kg per second how much steam is being flown. Then the blade velocity is given for means it is rpm is given 400 rpm, and what we need to calculate is we need to calculate the suitable blade height. Height, and as per the height, the diameter will also be fixed because it is a constant ratio of 12. And then we need to calculate the diagram power. Okay, so the vb in dm, so pi dn by 60, that is a standard formula, and d we are replacing by 12 hb since we need the value of hb, and accordingly we get this much blade velocity. And v1 is equals to vr2, right? Vr2, and that is why, and also there is some given the velocity of the steam relative to the blades at axis is 1.35 times the mean blade velocity. So 1.35 times the mean blade velocity, that is the condition given. Okay, so that is how we are getting this much value of v1. So at 1.2 bar, so the it was given that the expansion, the pressure is at the I think 1.2, expansion, the pressure is 1.2 bar and the steam quality is 0.95. So from that perspective, we just calculate the specific volume. Okay, the specific volume is 1.381 meter cube per kg. So why do we calculate the specific volume? Since we need the answers in the diameter and the height, so in length scale, so we need to consider the volume, not volume rate or not volume per kg. So we need to get the volume. So that is why we need the specific volume. So if we know the specific volume, that is volume per kg, or mass of the substance, so or the fluid, so then we can simply multiply the mass rate and to the volume. That would give us meter cube per second, right? So what is the volume flow rate of the steam that is given? So accordingly we can also calculate this. So vf1, okay, so what is vf1? Vf1 is the sine component. So this is the component of the steam that is flowing inside the turbine blades. So and what is this? Pi dm into hb. So that is particularly the area, area into velocity, that will give us volume per the volume flow rate. Accordingly we calculate the hb. So since everything is in terms of hb, right, all the variables are in terms of hb, we get the height as 0.138 meter. So accordingly we will get the blade velocity this much, and the inlet velocity from the nozzles is this much. Then if we know the inlet velocity and everything, so we can directly calculate the whirl component. So we need the diagram power, right? The diagram power is provided by the whirl component, which is responsible. So this is the vw we need to calculate. So simply v1 cos alpha minus vb, right? The from the inlet, this is the contribution to the whirl, and vr2 cos beta 2. Okay, so vr2 is equal to v1, right? We can directly replace it. And beta 2, so beta 2 is also equal to alpha. Okay, where is alpha? This alpha and this beta 2, this is equal. So accordingly we calculate and we get the world component as 53.28 meter per second, and the diagram efficiency you know very well. So omega, this mass of steam flowing per second into the world component velocity into the blade velocity. So this is 15.39 kilowatt. So this was one problem, but this is another problem of Person turbine that I have taken from the book. But since we are already past the time, I would like you to kindly solve this particular problem and check if you are understanding the Parsons turbine. And this is a very simple problem. So you just solve it, and I think we can stop the session for now, right?
सर
Hmm.
सर
Yes.
सर असाइनमेंट के प्रॉब्लम है उसके आंसर विद डिस्क्रिप्शन भेजो ना, वो कुछ कुछ आंसर गलत हुए।
Acha, okay. Then I will solve the assignment problems and I will send you that.
और सर एग्जाम पैटर्न कैसा है, मतलब डिस्क्रिप्टिव क्वेश्चन आएंगे या एमसीक्यू?
Actually, I am not sure about that. You need to discuss with the, I think the NPTEL committee. They will guide you better in this.
ओके
Okay. You just think that these kinds of problems will already come, and you need not worry too much. So if you are doing the assignment problems very correctly and you understand the concept, I think you will be doing very good. Okay then, so I will stop here the Parsons turbine, and we will continue in the next class. So I had a gas turbine problem also, so we will continue in the next class. Okay then.
Hello.
Please.
Sir, I have a doubt, sir.
Sure.
Sir, could you please move to the second slide, sir?
Second slide, right? Okay.
Actually, this is the diagram which is given in the book.
Yes.
I couldn't understand the physical nature of arrangement of turbines, sir. So in this diagram, I couldn't understand the physical arrangement of turbines, how it will be arranged like that, sir.
Physically.
Shows the nozzle moving blade and nozzle moving blade like that it is showing. But from physical point of view, I couldn't understand, sir, how these turbines are arranged and how the steam is flowing like that.
Okay. So these turbines are basically axial turbines. Okay, but axial turbines means the steam is moving in the axial directions. So what happens is that, yes,
These actually, you are talking about reaction turbines, sir?
I am talking about both the cases. Both the cases I am talking about. Okay, what happens is that if you see these particular blades now, so you think that these particular blades are actually in a circular manner. So I will tell you one thing. You have a rubber band, right? You have a rubber band. If you cut it in the middle and you place it horizontally, okay, you will see a straight line, right? But the components were actually arranged in the rubber band in a circular manner, but now you are seeing them in a straight line. So that is the case. So these are the blades which are fixed to the shaft, and it is in a rotative means circular manner, but we are actually observing it in a straight line.
Oh, okay.
Then
So this all this nozzle, this moving blade, nozzle, all are connected to the same shaft.
no, the nozzles are not connected to the shaft. The nozzles are connected to the casing above the shaft. So you are let me give you a visual idea. So there is a shaft, okay. You just small minute. So you have a shaft like this, okay. Maybe I can write it down here.
Yes, sir, it would be better if you draw the diagram, sir, if possible.
So this is a shaft, okay.
Okay.
Kindly do not mind my drawing. So this is a shaft, and here the blades are attached, okay. So these are moving blades, so this will be moving along this tangential direction, okay. So this is the shaft axis. Now you are having a casing also, Sorry. So you are having a casing which is actually taking this is not the, am I able to rub? So the casing is simply, it is holding the turbine shaft inside. So this casing is it is static in comparison to the shaft. Okay, so it will have some guides like this. Okay, again there is one turbine which is fixed to here. Okay, similarly here means it is in circular direction, so I'm just showing one projected part. So these are fixed. Okay, so the steam, it will have first a nozzle like this, a nozzle, the first one. So the steam will be like this coming. Okay, and it will striking the blade. How it is striking the blade? So the blade is actually, these are oriented in this way, you see, right? So the nozzle, it goes like this, and it the steam, it will flow like this. Okay, then again from the top, so from the top and top part of this here, and also it moves like this, the steam moves like this. Okay, so from the top actually it is loss, it's a loss, and it is called as shrouding. But you will be having a very good description on it on the videos. Okay, and the steam which is responsible for the rotation is the steam flowing directly through the turbine. So this direction you are seeing now, this direction. So actually this is the direction I'm talking about here.
Okay.
Okay, then it is again moving through a fixed blade, right? So this is the fixed blade. So it is also having some compartments from which the steam can move here. Okay, I'm drawing here. So the steam, it passed through here, and again it will pass through here, and directly it will go to the second turbine blades, second staging blades. Okay, so this is how it is moving in the fixed blade. But the fixed blade is it is connected to the this casing, right? So why it is called fixed blade? Because it is not moving now, the shaft is moving, right? So
Okay.
relative to the shaft, the blades are, these blades are fixed.
Okay, sir. Sir, actually, why do we have those kinds of multiple blades and multiple nozzles? Why not? Actually, there is a stage now from first initial nozzle is there, then multiple blade, then nozzle multiple blade, then nozzle multiple blade is there.
Right.
So why do we have these kind of different stages? Why don't we have one nozzle, one set of nozzle, one set of moving blade for generating power? Why do we have this kind of lengthy nozzle and moving blade stages?
Right. So that will be more better explained in this pressure and velocity diagram you can see here. So let me ask you this: the velocity has increased till here, then it has gone till here, but the total energy of the nth okay, let me again tell you here. So TS diagram, if I draw, then so this is the boiler part and this is the turbine part, right? So
Right.
here is the turbine. So if we induce only one this moving blades, it will come till only here, because most of the steam is going past. And just visualize, the steam moving this is also having a lot of energy, lot of enthalpy. So if you see this,
Extra energy is there.
so you just see in the HS diagram also. So in a HS diagram, the graph would be somewhat like here. This is the pressure process, right? So from here it is coming down S H. So only this part of energy is being utilized in first stage. But what about the remaining part? We need to expand from P1 to P2, right? So we need to expand it, right? So the pressure is still available. How can we see that? So here it is P naught, it is here P1, but we need the pressure to be down till P3, right?
Okay, okay. So by
So
utilizing full potential,
Because we need to utilize the maximum amount of this uh, the steam. Okay, only then we can get the maximum area under this curve, and the maximum area under this curve will represent the maximum work output or the maximum efficiency. But we are actually limited by this particular temperature and this particular pressure. Why? Because we are in the condensers, although it is vacuum, but we are cooling the whole the steam by nature lake water, right? So the nature lake water is having temperature fixed at around 30 room temperature, ambient condition temperature 30 degrees Celsius. And if we need to cool it, so obviously the temperature of this steam should be higher than this. There should be some temperature gap. So it is around 45, I think 43 to 45,
Okay.
and correspondingly the pressure will be 70, I think 7 pascal or something like that. So there will be some this vacuum, but we are restricted by this. There should be at least 10 degrees Celsius in order to effectively cool down. If we go beyond this, then there won't be any cooling, because the temperature of the thing where that we are applying the cooling water, it is having higher temperature than what we need to cool down, right? So that is why we cannot go even beyond. But if if it is possible to go beyond, we will use a lot of this staging, and we will go very lower than even possible.
Okay, sir. Okay, sir. Thank you, sir. Sir, one more doubt.
Hmm.
Sir, regarding the actually in impulse turbine, the arrangement of regarding the arrangement of nozzle, the nozzle direction will be perpendicular to the axis of rotation of shaft, right, sir?
Perpendicular, sorry, I didn't get you.
The direction of nozzle, that means the steam flowing direction
Huh.
will be perpendicular to the axis of rotation of shaft, right?
Axis of rotation of shaft. So this is the axis of rotation. Sorry, this is the longitudinal shaft axis. Okay, and about this axis it is moving like this. Okay, and about this axis you are having this particular blades in this direction. Okay, so the blade, so the steam will be actually passing uh, in this direction, the longitudinal axis of the shaft.
In axial direction it will pass.
Only then you can have this, na, because the steam will be passing here. Okay, just let me clear the screen. Okay, so this is the shaft, this axis. Okay, and here these are fixed, these are like this, these are fixed. Okay, and these are moving. Now you need to give a force in this direction, right? So what is the force, the force being delivered here? The force, the tangential force is being delivered due to the this steam coming in here and leaving here. Okay, so this will have a whirl component, VW, whirl component, right? This whirl component is responsible for the blade movement along the shaft, since it is giving a thrust to the blade. And the yes, yes.
So the wheel component is perpendicular to the axis direction, right?
More like to the normal to the blade, if you can see.
Normal.
See, the blade is like this, na. So
Sir, actually, in fluid mechanics, we say the Pelton wheel, right? Pelton wheel is there.
Pelton wheel is different. Actually, what happens in the Pelton wheel? So this is the case. So it
So
goes
the
like this.
fluid is hitting the blade. The fluid direction is actually perpendicular to the axis of rotation, right?
Hmm.
So
here it is like this, but here it is like so you see this turbine. So this turbine, uh, what is this kind of turbine? Actually you will read it in more depth in the next class videos. These turbines, but the direction here is directly impinging from this in the tangential direction, but here actually it is impinging like this. And due to the whirl component, there will be a whirl component here, there will be inlet component this vr1, and there will be a flow component or axial component va. The whirl component is actually responsible for this blade vb.
Okay, okay.
Okay.
Okay, sir. I got a bit of understanding. Maybe I will think some more time, sir. I will get clarity, I think.
Hmm.
Okay, sir. If I get doubt means I will ask, sir.
Sure, 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 sure.
Sir, if I want to ask you some doubt means how can I contact you, sir? Do you have mail or phone number?
My I think my mail id is given. um, Means I have already replied to a few of the doubts in the classes, but my mail id is uh, I will share my mail id in the discussion forum. I think it is already given there, but still I will do that.
Okay, 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 sir. Okay. Yeah. Okay, sir. Thank you very much, sir. Sorry for taking so much of time, sir.
No issues, no issues. No.
Okay.
Okay then.
Thank you very much.
Welcome, welcome.